Aidan, have made you co-host, so you should be able to do everything you want to do.
Okay, sounds good.
It works better if you're co-host rather than host for my recording. So if you have any trouble, does it seem like you're going to have any trouble?
I don't think so. Can you guys see the presentation?
Mm-hmm.
Okay.
Happy birthday yesterday.
Thanks.
Happy birthday yesterday.
Yeah, thank you.
I'll turn on my video in a bit. A bit on video all day. Do whatever you want and check whatever you need, okay? So that you feel comfortable.
Wait, hold on. I think I lost like control panel for the. Where the hell?
Did it get dragged somewhere you can't see it, or did you find it?
Yeah, I can't like click on it anymore. Wait, I'll just leave the meeting and rejoin.
Okay.
Okay.
Did it come back? You have what you need?
Yes.
I assume you just drug it too far and then you just lost it.
Yeah, I think it just disappeared.
Okay. Did everybody have a nice reading period?
That was pretty nice. It's kind of weird. I have Fridays off, so it doesn't really feels like every weekend it's reading period.
Oh, you're killing me. You're killing me. I definitely was excited for reading period. I needed reading period. We're making chocolate chip cookies for lab though.
What are you guys going to talk about? Like how like leavening agents work and stuff like that?
Not really. We're going to focus, since they haven't had to keep the lab notebook at all, we're kind of just doing lab notebook and experimental designy kind of things. There's not a lot of fundamental content. It's process lab, not a content lab. They have to bake 2 batches and change something, but the infrastructure for a lot of content was just not what we needed to do then. So I have marked Evan and Ricky, you have gotten your attendance. I think this is the first meeting for both of you. That wasn't your own. Ricky, your first talk, Evan, of your 5. Okay. I have 2 already down for you, Aidan. Daniel, you would have 3 if you were getting points. Okay, check you off. I got you on your attendance. This is number 2, not including your own. I can let the light in. You don't have to be able to see the whiteboard. Hey, Connor. Checking you off attendance. This is number 2 for you. Hey, Daniel. Do I do paperwork for reimbursement like normal, or is there a paperless system to do?
I have not dealt with that yet.
Okay.
I think the system is going to be the same. We just eventually have to get the receipt over to them. But the form, because it's electronic, I guess we can just, I don't know. I'd have to double check what they decided with that.
Do you want me to bring in the receipts to do it?
Say that again?
Do you want me to do it, or do you want me to drop off receipts tomorrow?
And just drop off receipts.
Okay, I'll put them to your bulletin board.
Okay.
Does that work?
Yep.
I think I have 3 different places.
Okay.
It was weird, yes. Nick, I have you number 2. Hi, Mike. Hey, Hallie, I have you. This is number 2. Katie, I will need to hear your voice or see your face or both to give you attendance credit. That's my deal. Today I ended class early in 116, and there were like some hangers on who clearly were no longer there, but pretending to be there. Thank you, Katie. If you want to turn it back off, you can. I just needed to see you.
Do we know who's introducing me?
Graham was gonna. So let's hope he comes. Just
Okay.
because I didn't prepare anything. I mean, I can certainly do it. Allison was supposed to be back up to that. So we will see. So Michaela, I will need to see your face or hear your voice to give you credit. Otherwise, you're good. I have you, frankly. I have you, Victor. Perfect, perfect. I have you, Michaela. See? There we go. Oh, it says my internet connection is unstable. That's awesome. So, Carl, I will eventually need to see your face or hear your voice. But otherwise, you're sort of there. Graham, I have
My connection's also unstable.
Gotcha. Got you, Carl. Is that correct, Graham?
What's that, Deanna?
Are you going to do the introduction?
I am, yes.
Perfect. Okay, well, I would like to welcome everybody to, I guess it's the third of the series of 20 of these talks. I'm really excited for the 5 talks we have this week. We're going to hear Aidan today. Then we have Maria and Evan going on Wednesday at 3:10 and then at 4 o'clock. And then we have Galini and Katie going on Friday. So we have a jam-packed week of talks here. And I hope that you're able to attend many of them. I think they're all shaping up to be great talks and full of a very wide array of research here. I'm going to pass it over to Graham to introduce our speaker for today. And with that, here is Graham.
Hello, everybody. Good to see you all here for another talk. I'm excited to introduce Aidan today. Aidan Delgado comes to us from Alicante in Spain, from as he told me just the other day, a small town on the shores called Torrevieja, I think is how he said it. I did my best Spanish accent there for you, Aidan. That's for you. Which sounds like a great town. I'm going to have to visit someday, I think. So I first met Aidan when he was a first year, and I was also a first year, as I said with Cade. This is my senior year as well. In Chem 116, several of you were in that same class with him, and those of you who were know that it is a testament to his and all of your perseverance that you're all still chemistry majors after taking Chem 116 with me at that time. So yeah, we struggled through 116 together, and for some reason after that, he came and asked me to do some research at some point. So I guess I must not have totally blown that class. And in fact, he spent a summer during the summer after his second year in my lab, working as Dan in the lab for the whole summer, again, persevering through a very challenging project. And after that, he was introduced to the magical world of quantum mechanics, and I think has been smitten ever since. And so he has spent another summer working in the lab of Randy Goldsmith, as he's going to tell us about today, and is now on his way out and headed to a different coast, going to UC Berkeley for grad school whenever grad school begins happening again. So with that, I will let Aidan take the floor and tell us all about these Weyl photonic crystals. Go ahead, Aidan.
Okay, thanks, Graham. So, hi everyone, and welcome to my senior capstone presentation. The title for my talk today is Weyl Photonic Crystals, Achieving Long-Range Interactions in Periodically Structured Photonic Media. Now, this title might seem pretty jargony at first, but by the end of this talk, you'll have a much better understanding of what this means. As I mentioned, I got to work on this project during my RU last summer at UW-Madison, where I was part of the Goldsmith group. If I were to describe the type of work this group does, I would say they do pretty interdisciplinary work, but always from a physical chemistry approach. While working on this project, I got to collaborate with different researchers, beginning with Thomas Mulholland, a postdoc in Tim Oswald's group, as well as Dr. Zhang Fu, both of which are in the engineering departments. My mentor for this project was Michael Maddy, a postdoc in the group, and finally my PI was Randy Goldsmith. Now, I want to begin by talking about the evolution of computers over the past 60 years or so, where in 1956, in order to store 5 megabytes of data, we needed a hard drive the size of an industrial refrigerator. Skipping forward to today, we can now store roughly 200,000 times more information on a micro SD card that fits on the tip of our fingers. And this is mainly due to our ability to pack more and more transistors onto smaller and smaller spaces, where a transistor is a semiconducting device that has a valence band, which is full with electrons, and a conduction band that has very few electrons. In between these two bands, we have a very small energetic gap, which we call the band gap. And this means that by inputting a small amount of energy into the system, we can have electrons jump between the two bands. And a good analogy for this is a switch, where by inputting a small amount of energy into the switch, we can turn it on. And this is what creates the zeros and ones in our computers, where 0 is a state of off and 1 is a state of on. Now, this leads us to Moore's law. In the mid-1960s, Gordon Moore, one of the co-founders of Intel, noticed a trend in the current technology at the time, and that was that the number of transistors we were putting on circuits was doubling roughly every 2 years. And this meant that our computers were getting faster and smaller at an exponential rate. And we can see this illustrated by the evolution of a transistor, where in the 1950s, this is what a single transistor looked like, and skipping all the way to the 2010s, on a similar amount of space, we can now fit roughly 8 billion transistors. Another way we see this illustrated is an evolution of mobile phones, where in 1984, Motorola introduced the brick, which had a 10-hour charge time for a 30-minute talk time. Skipping forward to today, we now have much smaller phones that have thousands of times the computing power. And nowadays, we're pushing Moore's law to the point where we're making transistors on a nanometer scale, which is very good when wanting to fit more transistors onto smaller spaces, but is now bad because by making transistors so small, they're going to start behaving quantum mechanically, where the electrons on our valence band are going to now experience a phenomenon known as quantum tunneling, where they can tunnel through this band gap without the necessity of any input of energy, which means that transistors can turn themselves on and off randomly without us having any control over them, which makes them useless to us. And this is why within recent years, we've seen Moore's law reach a plateau. This is an incredibly huge problem because this means that the technology that essentially powers every and this is where quantum computing comes in. Because quantum computing represents a paradigm shift of the way we understand computation and has the potential of fundamentally changing the way our computers can solve problems. where by combining the power of quantum mechanics with the way we store information, we can increase the processing power of our computers by many, many orders of magnitude, to the point where we can do things such as run extremely complex simulations, which is very useful in fields ranging from pharmaceuticals, developing new drugs, material science, when investigating new types of batteries, and even in non-scientific fields like financial modeling. And when we combine the power of quantum mechanics with the way we store information, we create what is known as a qubit. Now, before I continue, I should probably explain what quantum means. And in order to do this, I'll make the distinction between classical and quantum mechanics. So classical mechanics tries to explain phenomena from a macroscopic standpoint, meaning that it takes a top-down approach. And with classical mechanics, we can explain things such as our inclined planes, or we can figure out how far we can throw a ball, or where we have to stand to open a door. Quantum mechanics, on the other hand, takes a bottom-up approach, where it begins with atoms and investigates atomic phenomena. And from there, we can then build up and create models that best explain macroscopic events. In quantum mechanics, or quantum theory, is renowned to be a very complex topic, and that usually doesn't have intuitive pictures associated with them. But quantum mechanics is arguably the best theory we've ever come up with, because it can explain the most amount of phenomena with the greatest amount of precision, which leads us to ask, how can we apply quantum mechanics to computers? And in order to explain this, I'll again make the distinction between classical and quantum computers. For classical computers, use bits, which have two states of 0 and 1. And the way a classical computer works is that any image, any text, or any tweet that you see is simply a series of zeros and ones that encodes for some message. A quantum computer, on the other hand, uses qubits, also known as quantum bits. And the reason why we depict them like this is because we have a state of 0 and a state of 1 that are interconnected in a quantum mechanical fashion that I'll talk about in just a second. And qubits can be a variety of different things, such as photons, where depending on the polarization of our photon, we can have a state of 0 or a state of 1, or they can also be electrons, where we can have an electronic system with a ground state and an excited state depicting our zeros and ones. Okay. I said I'm muted by the host, sorry. And one key requirement is that our qubits have to be well-defined two-level systems. And an example of a two-level system is an electronic system where we have two distinct states. One depicted by our m(s) quantum numbers, which we typically call spins, where we can have an electron with a spin up or an electron with a spin down. And the reason why qubits make quantum computing so powerful is because when we have a connected group of these qubits, these have orders of magnitude more processing power than that same number of classical bits. And this is due to a quantum property known as superposition. What superposition is the ability of a qubit to be in both a state of 0 and 1 at the same time. And when we have a qubit in this state of superposition, and then we take a measurement on it, what we're doing is collapsing that superposition into either a state of 0 or 1. And a good analogy for this is Schrodinger's cat, where we can have a cat inside of a box that is both dead and alive. And once we open the box, aka take a measurement, the cat is now either dead or alive. And the reason why superposition is such a powerful tool is because of the way these computers solve problems. Where we can take this maze, for example, to be the problem we're trying to solve, a classical computer will go about doing it by solving every possible solution one at a time until it reaches the correct answer. A quantum computer, on the other hand, can solve every possible solution simultaneously due to this property of superposition, which makes it so it can arrive at the answer much, much faster. And to put this into context, if we had a system with 64 different qubits, this means that we have roughly 18.5 quintillion possible states. And for your classical computer to run through every state one at a time, it would take it roughly 400 years to do so, going at a rate of 2 billion states per second. A quantum computer, on the other hand, can do this in a matter of minutes. Now, when talking about quantum computing, we also have to talk about quantum networks. Because the same way we have classical networks where we have an interconnected system of computers, we also have quantum networks where we have an interconnected system of qubits, where we need these qubits to be able to communicate with each other. But these quantum networks have one major problem, and that is that the interaction between these qubits decays exponentially as 1 over r to the 6th, where r is the distance between two qubits. And this means that even if we have two qubits at relatively short distances, the interaction between them is going to be very, very weak, which means they can't communicate with each other very effectively. And this right here is a problem that our project is trying to tackle, where we want to make qubits able to communicate with each other at longer distances. Now, before I continue, I want to introduce a new term, and that is isosurface. Iso from the Greek meaning equal. This is a surface that represents points of equal value. And for this talk, I'll be referring to momentum isosurfaces, meaning a surface that represents points of equal momentum. So now moving on to qubit interactions. Imagine we have two qubits separated by some arbitrary distance. We can denote the interaction between them by the letter gamma, where this interaction is defined by this integration. And the only thing you guys need to take away from this is that the function inside is oscillating, meaning it's going back and forth between positive and negative values, which means that as r increases, where r is the distance between the two qubits, the interaction is going to decrease, where when we have two qubits at a large distance, and we then project this function on the isosurface that describes the system, we're going to have a lot of these oscillations projected on it, where the orange and blue bands are going to be canceling each other out, and therefore giving us a weak interaction. On the other hand, if we have two qubits separated by a short distance, this means that our function is not going to oscillate nearly as much. Which also means that when we project it on the isosurface, there's not going to be nearly as much cancellation, and we therefore have a stronger interaction. And this is why in chemical systems, when you have two molecules separated by a large distance, they interact very weakly, but if they're separated by a very short distance, they interact very strongly. And just recapping, if we have two qubits separated by a large distance, we're going to have a lot of oscillations projected on our isosurface, which is going to give us a small gamma value. And this is why our interaction decays exponentially. So here's the hypothesis of this project. And that is that if we are able to create some medium in which we can have this interaction occur, this medium is minimizing the size of this isosurface, meaning it's making it really, really small, we can then achieve longer range interactions. And this is because by making this isosurface so small, when we then project the function on it, a minimal portion of that function is going to be projected on the isosurface, which also means that we're going to have a lot less cancellation happening, and therefore we're going to get these long range interactions. And one way to think about it is that if we have our isosurface, our normal isosurface, and then we just take a little chunk out of it, that is what the smaller isosurface is representing, where we now only have the orange band and none of the blue band contributing to that cancellation. But the question now is, what sorts of systems can we use to decrease this isosurface? And one possible system that we want to investigate closer are biophotonic crystals, where photonic crystals are materials that have a periodic dielectric constant. And a dielectric constant simply is how well an electric field can permeate a material. And this periodicity can be in 1, 2, and 3 dimensions. And since we're dealing with crystals, we're also going to have their associated band structures. And a band structure, or all of these blue lines, represent all the possible energy levels where electrons can hang out within this crystal. And if we take a close look at this plot, you'll notice some pretty strange coordinate systems on the y-axis, on the x-axis, and these are called Brionzone coordinates. And essentially, these are just a bunch of random Greek letters that we use to describe the unit cell of the crystal. So the unit cell is the smallest possible repeating unit within this crystal. Looking at the y-axis, we have frequency, which means that the energy of the electrons in these bands is directly related to a sort of frequency. Now, a couple of things to note about these photonic crystals. The first thing being that the structure of the unit cell is going to heavily determine what the band structure looks like. Where here we have two very distinct unit cells, and we therefore have two very different looking band structures. Another thing about these crystals is that the size of the unit cell has to be lambda over 2, where lambda represents the wavelength of light, which we can also interpret as a frequency at which we're going to be interacting with the electrons at certain bands. And since the wavelength of light can span many orders of magnitude, so can our crystals, where we can have crystals ranging from a micrometer scale all the way to a meter scale. Now moving to biophotonic crystals, these are essentially the same thing, but we're now adding the nuance of having a point of degeneracy, meaning of equal energy, between two bands in this band structure, where the point where two bands are crossing is called the Weyl point. And the way we make one of these Weyl points is by breaking the inversion symmetry of the crystal. And for those of you who haven't had Chem 320, inversion symmetry simply means that if we have a symmetrical structure and we then invert every point in space of that structure, if it continues to be symmetrical, it has inversion symmetry. And most times, these photonic crystals do have this type of symmetry, where here on the left, we have a two-dimensional crystal that is perfectly intact and therefore has inversion symmetry. And here we have its corresponding band structure, where we have a band gap between certain frequencies. However, if we introduce a defect into this crystal and we therefore break this inversion symmetry, we create what is known as a defect mode. And this is what gives rise to our Weyl points. And the idea here is that the closer we get to our Weyl point, the smaller this isosurface is going to get. And this is because biophotonic crystals have what is known as a conical dispersion relation. For this right here is a 3D rendering of a band structure. And as we get closer to our Weyl point, right there, our isosurface is going to diminish to a singularity, meaning that it's going to keep getting smaller and smaller. Now, specifically looking at the crystals we want to make a Weyl crystal that has a double gyroid structure, and we want to introduce our defects in the form of an air sphere. And for every defect that we introduce, we're going to be creating one Weyl point. So since we have 4 defects, we're going to be creating 4 different Weyl points. For the closer we are to that Weyl point, the smaller that isosurface is going to be. So at point 1, we're pretty far away from that Weyl point, which is why our interaction decays fairly fast, and we have pretty large isosurfaces. At point 2, we're a bit closer now to the Weyl point, which is why our interaction persists a little bit longer, and our isosurfaces are a little bit smaller. And finally, at point 3, we're now the closest we are to the Weyl point, which is why our interaction now persists the longest, and we have very small isosurfaces. So now that I've covered the theory behind these crystals, I'll move on to talk about the way we want to make them. And one thing to note is that the frequency of the Weyl point, meaning where it is vertically on this axis, directly depends on the dielectric value of the material that we use to fabricate it. Where the higher this dielectric is, the lower the frequency of the Weyl point will be. Another very cool thing about this project is that we wanted to 3D print this crystal. And this is because we want our Weyl point to be in the frequency range between 2 and 3 gigahertz, which happens to be the same frequency that microwaves are in. And since microwaves are really big waves, and we have that condition of our unit cell being lambda over 2, that means that our unit cell is also going to be pretty big, which enables us to 3D print the crystal. But in order to print it, we need plasticity, meaning flexibility in our material. And given these requirements, we came up with the following formula, where we have ABS, which is a pretty standard polymer, and it's what Legos are made out of. We also have barium titanate, which is a very high dielectric material, and we added that with the hopes of increasing the dielectric of our overall composite material, as well as cobalt ACAC, which was the source of cobalt ions, which would again increase our dielectric. And finally, stearic acid, which is a plasticizer, where these long carbon chains add flexibility to our material. Now, before we 3D print anything, we have to make sure we have good dielectric values. And in order to do that, we take our 4 components and we put them inside of a torque rheometer. And this machine right here essentially does 2 things. It heats up and it mixes, where we have a little chamber that we usually heat up to about 200 degrees Celsius, and then we pour in all of our components, and then it begins to mechanically mix. And from our torque rheometer, we obtain an amorphous composite material. But in order to measure the dielectric, we need a very uniform sample. And to do that, we take our composite, we put it inside of a compression molder, which is this blue machine right here. And the way we do this is we take our composite, we put it inside of a mold, and then we place the mold inside of the machine, which heats it up to make the material more malleable, and then it applies extremely high pressures. And from our compression molder, we obtain a sample that looks like this. And in order to measure our dielectric, we then use an LCR meter. or we can measure inductance, capacitance, and resistance values from our composite. And then we can apply this equation right here to calculate our dielectric, where epsilon is a dielectric, thickness is of the sample, and we have the capacitance that we just measured over the radius of the electrode on the meter, and the dielectric value of vacuum, which is a constant. So now that we have our dielectric measurement, the next thing to do is to 3D print the crystal. And in order to do this, we take our composite and we place it inside of an extruder, which creates a little filament out of our material, which we then feed into a 3D printer and print our crystal with. So now that we have a 3D printed crystal, the next question to ask is, what qubit should we use? But a better question here is, what makes a good qubit? There are three main requirements. The first one being that it has to be a well-defined quantum two-level system, which I talked about earlier. The second one being that we need long superposition lifetimes, meaning that we need our qubits to be in that state of superposition for as long as possible in order to perform the desired calculation. And third, we need our qubits to be optically addressable, which means that we need to be able to manipulate the state of the qubit with some form of light. And given these requirements, we decided to go with nitrogen vacancy centers. And what these are within a diamond lattice, a missing carbon atom, hence the vacancy, in which next to these vacancies, we have naturally occurring nitrogen impurities. And the reason why we chose NV centers is because they have very long superposition times on the order of milliseconds, which is very good for these sorts of systems. And they're also optically addressable, specifically using microwave pulses. So now moving on to some of the results that I obtained, and I don't have too many of them. But before I talk about those, I want to talk about specifically how I contributed to this project. And the first thing I want to mention is that I took on this project with my mentor, Mike, from the very, very beginning. So this was a completely new project and no previous work had been done on it. The way I contributed to this project was that I made the material that would be used to 3D print the crystal. And by making this material, I obtained two main sources of data. The first one being band structure simulations that I did using a package in Python, and the second source of data being the dielectric measurements of the final composite material. So now moving on to band structure simulations, there are two main variables I changed. The first one being the dielectric constant of the material, and the second one being the radius of the defect. So when looking at these simulations, a couple of things to note. The first one being the dielectric constants are unitless, which is why I don't have any units right here. And a couple of things that we're looking for in these simulations are first, obviously, Weyl points, which we'll see around here. And we want these Weyl points to be well isolated, meaning that we don't want any other bands being close to them in terms of frequency. We're also looking for Weyl points that have an X shape, which are called type 1 Weyl points, and not Weyl points that have a T shape, which are called type 2. So now looking at the simulations, with a dielectric of 10, we do have some Weyl points there and there, but they're not well isolated because we have other bands near them. So increasing the dielectric helped. We're now at 16. We have some pretty good Weyl points, which are pretty well isolated and have that desired X shape. As well as at 20, we also have pretty good Weyl points. But as we increase this dielectric at 23, we're now starting to see some of that T shape, which means we're starting to see a type 2 Weyl point. And finally, at a dielectric of 30, we definitely have type 2 Weyl points, which we do not want. Moving on to the radius of the defect, this number right here simply represents the percentage of defect with respect to the size of the unit cell. So 0.07 is a 7% defect. And at 0.7, we already have some pretty good Weyl points, which are pretty well isolated and have that X shape, as well as at 0.16. And as we start to increase that radius defect, our bands start to smush together and we're now losing our Weyl. So based on these simulations, we determined that a dielectric between 11 and 20 would be best, and a radius defect of 0.07 would also be ideal. And this was for structural purposes, because the bigger this radius defect, is, the more less structurally sound the crystal will be when we're printing it. So now moving on to dielectric measurements, Here's a plot of some of the data that I collected, where we ran Teflon and ABS samples just as a standard to make sure that the LCR meter was working properly. And we made these Teflon and ABS samples the same way we made our composite samples, which was by compression molding. And when looking at the Teflon data, we noted that it was pretty close to the literature values, which was good. But when looking at ABS, it was a bit lower than we expected. It should have been between 2.5 and 3.2. And when looking at the plot, it's around 2. And we thought this might be due to some air gaps in the sample. And this is because when you compression mold, sometimes you can get little voids or air bubbles inside of your sample, which can throw off those conductance measurements and therefore throw off your dielectric calculation. With respect to the composites that we made 2 different ones. The first one being 5% by weight cobalt ACAC, and the second one being 10% by weight. And we had literature supporting the idea that the more cobalt ACAC we had, the higher the dielectric would be. But this turned out not to be the case, as you can see right here. And we don't really know why. And this might be something worth looking into a little bit more. But the main takeaway from this plot is that we can make a material that has a dielectric above 11, which was that minimum requirement that we determined based on our simulations. And this means that we have a material that we can 3D print a crystal with. Sadly, this is where my RU finished. So I didn't get to work on this project any longer. We're now moving on to the next steps of the project. Obviously, the first thing would be to print the structure. And once the structure is printed, we would then need to collect some band structure data. And we do this by performing multi-angle microwave transmission measurements, where we have our crystal in a setup which we can rotate through different angles, and then we shine microwaves through it. And what we're detecting is the transmission of these microwaves to the crystal, which would give us data that looks something like this, where we can then determine at what angles we have a Weyl point. Or right here, and at a rotation of 90 degrees, we do have a Weyl point where we have degeneracy between those 2 bands, but at 105 and at 120, we no longer have a Weyl point because the bands are no longer touching. Finally, in concluding, what have we learned? Well, we now know that quantum computing has the potential of fundamentally changing what is computable. We know that qubits gain their power from their ability to be in the state of superposition, and in order to enable quantum computing, we're going to need quantum networks. These quantum networks have this problem that the qubits cannot communicate with each other at long distances. And one way we might be able to mitigate this problem is by using biophotonic crystals, where by minimizing the size of this isosurface, we can then achieve long-range interactions. Lastly, a couple acknowledgements. First, I would like to thank UW-Madison for allowing me to participate in the REU program, as well as the NSF, DARPA, and MERSEC for funding my projects. Obviously, I'd like to thank all of you today for listening, as well as the Goldsmith Group for teaching me everything I learned last summer, the UN Oswald groups for helping me with this project, and lastly, and most importantly, I'd like to thank my peers and professors for teaching me everything I've learned over the past 4 years and helping me become the chemist I am today. Thank you very much, and I'll take any questions.
Thank you so much, Aidan. I was trying to clap very loudly. I guess Aidan will take any questions.
Were there like connection problems?
Yes, there were. But that's why I kept muting you to get you back on track. So
okay.
I tried to do it while you drink your water.
Oh, okay.
To do it, so that's what was happening there, but you were ahead of yourself.
Okay.
So I was trying to get you back on track. Per Graham's suggestion. So blame Graham. Questions? Raise your hand, just speak up. There's lots of you, so I can't see you all.
Yeah, so just how would you actually implement the 3D printed crystal into some sort of computer system? Because you said that it could be used, but just I'm trying to visualize a actual physical way of implementing it.
So the field of just quantum information science and quantum computing is very, very new. And these are just trying to tackle some of these basic problems. So right now we can't have qubits interact at long distances. So that we're just trying to investigate new systems that can allow us to do that. Specifically, I don't think you would see this in a quantum computer because like it wouldn't like work with a quantum computer, but this is just one way of enabling interaction between two qubits. And some potential applications can also be like if you're able to entangle two qubits at long distances, we can also use these systems. And when I talk about long distances, the scales are still pretty small. Like when I say like two qubits can interact at close distances, that's like nanometers or less, right? So when I say long distances, I'm referring to maybe micrometers. So we're increasing by order of magnitude.
I think Victor had a question.
I was about to ask the same thing.
Okay.
I have a question.
Oops, sorry. Go ahead, Nick.
All right. Could you go back to your band structure simulation?
Yeah, like my data?
Yeah. Because I noticed that there was like what I would think is another Weyl point in a different zone. So I was wondering if that was actually if it is a Weyl point, like in that N4 zone, where the
Right
bands,
here?
yeah, where it's like crossing. So I was wondering if that if that's considered a Weyl point and whether that can be connected to the other Weyl points.
Yeah, so this would also be another Weyl point. So any specific, just any point where two bands are crossing is considered a Weyl point. So I was just talking about these right here, but this would also be a Weyl point.
Okay, would it be like beneficial to have more?
So for every Weyl point you have, you're gonna have, you're gonna be decreasing your iso surface. Let's see. So I guess, I mean, yes, the more Weyl points you have, the more, sorry, actually no, because this persistence and interaction at longer distances is just for every Weyl point. Because I didn't get into this, but like these Weyl points have another benefit to them is that the direction of the momentum dipole of the qubit doesn't matter anymore because they're isotropic. They extend the interaction isotropically, meaning in every direction. So for every, I guess, actually, I don't know. I guess if you have more Weyl points, I don't think that would necessarily be that much better if you're not controlling them. But I guess my short answer is I'm not sure.
No, that's good. Thanks.
Carl, did you have a question?
Yeah, I was curious, like for the materials that you end up putting in the extruder, how are you certain that they're consistent all the way and don't have any like impurities or anything like that while you're using them? Like what's the process?
So you mean like how can we make sure it's homogeneous?
Yeah.
Or, so I mean, it's essentially, so the way we did this, we didn't actually put every single component individually into here, where the way we did it, we first dissolved ABS and acetone, and then we mixed it with the cobalt ACAC, and it's like, this cobalt ACAC is like very green powder. So we essentially just have like this green kind of like slushy-ish material, which we then dried out into like these flakes. And then we added that into the torque rheometer and combined it with the steric acid and the barium titanate. I mean, and we let this run for a couple hours. So, I mean, it mixes pretty well. These wheels that essentially just crush everything and mix it over and over together. So yeah, I mean, it's pretty homogeneous. When it comes out, it all looks like one homogeneous thing. So yeah.
Other questions?
Could you go back to the simulations again?
Mm-hmm.
I was just wondering if there was any impact of there's like vacancy radii on the dielectric constant, and if so, is there any reason to run simulations where it tries to optimize both of those parameters at the same time?
Your question is the fact that we have a defect affecting this dielectric value?
Yeah, so like, do they affect each other? Or like because it seems like you optimized them separately. So I'm just wondering if there's any reason that like you would want to optimize them together or try to run a more complex simulation on the bandgap structure.
So the simulations I'm showing here, these are like the best ones I have, because I ran hundreds of simulations where I was optimizing every parameter. So I started with the dielectric, and once I found the best dielectric, then I started tampering with defect radius and some other parameters. So this right here is actually a combination of how defect radius is changing with the best possible dielectric value. So I've already like optimized the values, and then I go back and then I change one variable with all the optimized values, and then I go through all of them like that. But then also the radius of the defect would actually not affect the actual dielectric value. It would affect what the band structure looks like, but a dielectric value is intrinsic to a material, so that wouldn't change. So like the fact that it's 30 wouldn't change at all. What would change is the band structure.
Other questions? Graham?
So Aidan, I'm trying to understand how this works. You showed a little picture of the double gyroid structure you wanted to make, and then you showed that there were 4 defect sites, little bubbles that you kind of drew into that structure. So is it the case that you basically print this crystal and you keep making that same unit cell, and there's a bubble in the exact same spot for every unit cell? Is that right?
It's not in the exact same spot, because if it was if it was in the exact same spot, you will be creating the same Weyl point. So if you look at this structure right here, the defects are not like these. So like they're like paired. So like there's 2 gyroid structures which are like intertwined, and this one and this one are the same, and this one and this one are the same, but they're not within the same gyroid. They're not in the same spot.
Right, but then as you make this crystal, you'll always have a defect in the same point in the unit cell. So you'll have 4 defects in every unit cell of the crystal as you continue to propagate, or is it only in one of the unit cells for the whole crystal?
I think it's throughout the entire crystal.
So your 3D printer, you essentially put that little diagram in, and it knows to just keep repeating that same thing over and over in 3 dimensions.
Yeah. That's some pretty hefty 3D printers there. They were like huge. They were like the size of, like, you can't see that, but the size of this bedroom. And they also were super precise, where they had like a 0.5 millimeter precision with printing.
And had ventilation, so you could put whatever you wanted in it, unlike ours. Other questions?
Mm-hmm. Yeah.
Okay. I'm not seeing any questions, but there are a lot of you. But thank you so much, Aidan. If we could give Aidan a round of applause. And I'm sure Aidan would be happy to answer any of the questions that you have, if you wanted to hang around and ask them one-on-one. But thank you so much for attending, and I hope to see you later this week on Wednesday or Friday for some more great talks. Let the Zoom awkwardness continue.
Great job, Aidan.
Thanks.
Good job, Aidan.
Okay.
Sorry, I misunderstood the video mute, Graham. I just misunderstood. I'm not operating on all cylinders.
No, that's okay. I was just an idea.
So what exactly happened?
Your slides were a little behind your audio is all.
Oh, okay. Because I kept seeing like, you've been muted when I was talking, and then I was like confused.
Yeah, I was trying to suggest to Deanna to turn your video off to help you. I almost chatted you instead, but I didn't want to disrupt your flow. So
Okay. Well,
It was not that bad, and it was fine. You were fine. It was good.
okay.
You did a great
absolutely.
job. Nothing to
Yep,
worry.
you sure did.
Thanks.
I liked some of the changes at the beginning too, and the end. So I was very happy.
Mhm.
You should be
That
proud of
was
it.
really, really cool stuff.
Yeah. Not too many questions though, but that's okay.
I think just too far outside of people's wheelhouses.
Yeah.
Not
I was thinking of maybe making a slide of like suggested questions.
Not a bad idea. I so the microwave travels through the whole crystal, right?
Mm-hmm.
But does it bounce off of the, because your void space in the crystal is one dielectric, and then the material itself is the dielectric you chose. So
Mhm.
does that cause reflection of the microwave through the crystal, or is it just kind of, just penetrating through the crystal but slowing down in some places and not in others?
I mean, I'm not